Well, I'm back now for a second try at making this video. My first one kind of crashed and burned, okay? It's very seldom that I ever have to redo a video because I generally want to just go from go and just teach as if I was still in front of you, in front of the class. Problem is that I wanted to show you the game Angry Birds. I don't know if you haven't seen this game yet, but it's phenomenal, okay? It's like this game where you take like this little slingshot thing and these birds and you like shoot them and then they go flying across the sky. And the neat thing is that there's little dots that get placed on there that follow this kind of nice little curve, and it's a parabolic curve, and then it hits something, okay? And you're trying to smash the little things and get the pigs apparently. Now, I don't know how many of you have played this game before. I heard that it's kind of a big thing right now. I've seen t-shirts in Target. My son, who's 4, comes home and can point out things. It's Angry Birds. And the thing is that is nothing more than projectile motion in video game format. And it's very kind of interesting because, again, that's the topic of what we're talking about, is projectile motion. Now, the thing is if you've played the game, you know that there's kind of like 2 angles that you can go at. Like you can pull the bird back and you can go at a very low angle and get to the same spot, or you can pull the bird back and you can go very steep angle and get to the same point. And either way, you get to the same point. And so there's always going to be that 2 angle thing that's going on, and it's because we have 2 different dimensions that we're working with, and we have a quadratic equation involved, and so that's why we always have this, okay? It follows that parabolic curve, which is the exact thing that we expect to see in a quadratic graph, okay? And so we have 2 solutions usually for any of those types of things. All right, so enough discussion about Angry Birds, because again, I could get lost playing that game for a while. So let's talk a little bit about projectile motion. Now, I happen to be a little bit of a photography buff on the side here too. I've shown, I think, a couple of the pictures that I've been taking, or you've seen me take pictures. And this is an interesting one, and I wish that, I haven't done one to show this parabolic motion yet, but this is basically taken where every frame represents one image of our guy on the motorcycle. And then they layer those frames together in Photoshop to give us the kind of effect that shows us how the motion is being tracked. It's a lot like what we were doing with our video analysis, where we put our dots on and then we advance a frame. So every picture represents a frame, and every frame represents some kind of motion. And what we can see here is we see that the motion in the x direction, so I'm going to say this is my x direction, is fairly consistent. So in other words, the distance from here to here is about the same as the distance from here to here, which is the same from the distance of here to here, and here to here, and here to here, and here to here. So when we start to look at this, we look at this in terms of a motion problem in one dimension here, the x direction, and a motion problem in the direction of this way. And so we start to say, how does the motion behave? Well, all of our motion in the x direction seems to be fairly constant. Okay, and we see that we have constant velocity in the x direction because the position seems to change at the same point. Okay, if you remember, we do our little graph. This would give us the dots that would look like this in a position time graph of the x direction. Now in the y direction, we see that we have our point here. So I'm going to start picking a point on my motorcycle, a point on my motorcycle, and a point on my motorcycle, and a point on my motorcycle, and trying to get the same point on the motorcycle each time. You can see that we have a bigger gap from here to here, and the gap gets a little bit smaller, and a little bit smaller, and a little bit smaller, then it gets a little bit bigger, and then it gets a little bit bigger. So we can see that from, like, say, this point here to this point here. So in other words, here to here, we see that our gaps are getting a little bit smaller each time, okay? And then on the other side, we see that the gaps are getting a little bit bigger. This is accelerated motion, okay? And so we can see that in the y direction, we have probably constant acceleration. So we have 2 components that are going on. Now, and I don't know, my picture is probably on top of the ramp, but the ramp is set at a various angles. So in other words, there's an angle that's going this direction as the motorcycle leaves. That means that his velocity initially is at some particular angle. So he has a velocity vector that's at some angle. Now, because we have a velocity vector that's at some angle, and we've been talking about angles and splitting these things up, we can see that there's a component of this that is a velocity in the x direction and a velocity in the y direction. And that would represent initial velocities in each. Now, in the x direction, everything remains constant. So this is a constant velocity. It doesn't change. Everything is defined now by d equals vt. That's my situation. It's my constant velocity equation. In the y direction, though, we see that our displacements are changing. So again, we're showing something that looks more like this. Our displacement was big displacement, gets a little bit smaller each time, and so we see something that looks like this, okay, before it starts to spread itself back out and come back like this. So you can see that we get a curve through this portion, and a curve there in a position time graph says that I have constant acceleration. Well, that leads me to the other three equations. So the other three equations are the constant acceleration. If we look at this problem in particular, this y direction is nothing more than a falling object problem. It's a falling object or a throwing object up. It's a gravity problem. It's a free fall problem. Okay? And so that's how we kind of look at this. We look at it in two directions. We see each point on the motorcycle, we have a velocity in the x direction, we have a velocity in the y direction, and this is probably getting smaller. Hold on. Okay? In the original one, we might have velocity in the y direction, velocity in the x direction. Okay? The velocity in the x direction never changes, but the arrow gets smaller as we go in the y direction. Now, the key thing is that at this peak, this is probably our point where we no longer have any velocity in the y direction. We have everything going in the x direction. Okay? So this is projectile motion. It's about looking at velocities and in two different directions and how we kind of split them apart. So again, this is going to be kind of some of the terminology that we need to know. We always like to know things about the maximum height. Maximum height is when our y velocity is equal to 0, okay? And our x velocity is just our x velocity. And in the x direction, we always refer to that as having constant. So our distance here is what we call a range. So we have heights now, and then we have ranges, and we have to understand the difference between the two. A range is always dealing with something in the x direction, and a height is always dealing with something in the y direction. The nice thing is that everything occurs at the same time, okay? So the time of flight happens at the same point. Now, here's how we equate time, okay, into this, is that the time of flight is the time that it takes to get from here over to here. The time to get to the maximum height then is actually half of that time. And we call the time of flight, or we can refer to this as the hang time. Okay? Hang time is the time to get from this point to this point. And then there's the time that we want to get to our maximum, and this is like a half time. So if we take that hang time and divide it by 2, that represents the time that it takes to get to the halfway point. So there's a relationship now that we build into looking at graphs that look like this. Now we have direction changes that occur here. Okay, essentially our velocity, our initial velocity going this direction, is going to experience an acceleration that's in the negative direction. Okay, because we tend to always choose the upward direction as the positive direction. And then remember that when we get to this point, all of a sudden we switch, and our velocities now start to switch over. And sometimes when we work these problems, we actually split these problems into two parts. Okay, and so I'll refer to the part going up or the part coming down. Okay, because it's how we try to treat these problems. Just to kind of look at typical situations for projectiles, we kind of have two unique situations. The first one is this one where we actually have, say, like a car falling off of a cliff. Okay, so this is my cliff jumper here. all of my original velocity was in the x direction. So I put all of my original velocity in the x direction. It's now a dropping problem, so it drops in the y direction due to gravity. And we are actually looking at like half of a parabola. Okay, so that's my half of a parabola situation. We tend to treat the downward direction as the positive direction, so we then look at it from the standpoint of as we're increasing. So that's my cliff problem, jumping off of a cliff or driving off of a cliff. The other type of problem that we look at is the one where we're aiming and we're raising or lowering our cannon. So we're actually looking at it where our original velocity is placed at some angle. And the moment we leave the barrel, it shoots up, but then its velocity starts to change and decrease until we get to that highest point, and then we continue on our path as we go. So there's kind of two different scenarios that we look at. We're going to do something with our Hot Wheels on this one. Okay, so that's going to be a Hot Wheels type of a problem. And the projectile ones will probably try to launch something. I don't know exactly where we're going to go with that one. But those are our two main types of problems that we look at. And I think what I'm going to do here is I'm going to pause at this point in time so that you get a chance to kind of understand this. There's a couple of good web resources that I might say you should go look at. In fact, let's see if we can jump over there since I got a minute or two here to look at. This is always the tricky part, is anytime I want to do something like this. I'm going to try to end my show here. Discard that. And go back here and go to School Docs. We'll see. If I run out of time, that's okay. But I do know that there's a couple of simulators or things that we could look at that'll be good for us to look at. Anyways, I think I'm going to pause it. We'll talk again more tomorrow. And again, if you're good at Angry Birds, you already have an understanding of how projectile motion behaves, and we'll be able to talk more about projectile problems in the next video. So tomorrow night's video will be on projectile motion problems. Until next time, happy physics.